So the red blood cells right here, found in higher concentration in male than female. The main purpose of red blood cells is to carry oxygen, right? That is the main purpose. At the same time, it also has enzymes that allows you to carry other gases. So we're gonna see a third of the components, a third is a hemoglobin. Now, when we look at hemoglobin right here, and number one, all right, we'll talk about that in a second. All right, when you look at these red blood cells, they are very wide at the edges and very thin in the middle. There's a reason for this. Right? Take a look at how thin they are in the middle here. The reason is simple. As red blood cells goes into the capillaries. Remember, right, when blood exits your heart, it goes into this huge blood vessel we call the aorta, right? And then you distribute it to smaller arteries. And then eventually you go to your target tissue, and in order to get blood to the muscles or your lungs or anything else, you need to send that red blood cell through a very small, very thin capillary. As it goes into a capillary, the red blood cells have to go single file. That's how small the capillaries are. Sometimes the red blood cells have to be pinched, right, to go from one side to the other. When you have a normal red blood cell like this, you can imagine it's easy to pinch it to get from one side to the other, right? Now, some of you might have heard of this disease before. Sickle cell anemia. Right? When you have sickle cell anemia is what we call an autosomal recessive disease. You need two of the bad sickling genes for you to have the full-blown disease. One from each parent, right? So dad gives you the sickle cell gene. Mom gives you the sickle cell gene. Now you're homozygous for it. And now you have the full-out sickle cell disease. Why is this important? People with sickle cell disease undergo sickling, right? Where the red blood cells, instead of having this nice small middle area, right, the plasma membrane of the red blood cells sickles, becomes C-shaped, right, and hard. And what happens? You can't bend those cells. When you can't bend the cells can't get through from one side of the capillary to the next. And what happens? It acts like a blood clot. So that sickling occurs, and now you have blood clots that can occur anywhere. And even now, the treatment for sickle cell anemia is just pain meds and fluids, all right? And sometimes I'm anti-inflammatories. That's it. There's nothing really good for the treatment. And even now, people that have the full-blown disease, the lifespan is in the 50s. That's it. That's severely lower than what we see in a normal person. So that's why sickling and sickle cell anemia is so important. Now the trait, you can still have sickling if you have sickle cell trait. That means you have one good gene, one bad gene, right? You can still have what we call a sickling crisis. A sickling crisis are those blood clots that form everywhere. When you have the trait, you need other things to kind of add on to it, right? When you have the full-blown disease, you don't even need anything. You just have sickling crisis because almost all of your red blood cells are sickled. When you have the trait though, usually if you're nice and healthy, you're not gonna have any kind of sickling crisis, no clots. But if you are dehydrated, but if you are at, living at high sea levels, well, those two conditions can cause people with the trait to start sickling. The best example I have of this is a football player. A few years ago, he played, now he's a commentator, but he played for the Pittsburgh Steelers. And what he did was this, right? You guys remember a few years ago, I believe like in 2013, Tim Tebow had that touchdown pass, right? Against the Denver Broncos or against the Pittsburgh Steelers. Well, the person that should be playing that position, Ryan Taylor, the year before, he found out he had sickle cell trait. And he played. And what happens is this. What happens when you play a lot and you're in there a lot, is you start to sweat. As you start to sweat, your blood, the amount of water in the blood starts to drop. Your blood pressure starts to drop. at that point, it's harder to push those cells through the capillaries. He started to sickle as a response to that. Right? Now, he was playing in Denver, and when you're in Denver, you're at a mile-high city, higher elevation, less oxygen. The higher the elevation, the less oxygen in the atmosphere. The less oxygen causes your blood vessels to constrict. So now the worst case situation happened. He had lower blood pressure because of dehydration, and the blood vessels that should be big and open now started to close up. As the blood vessels start to close up, and now you have no more pressure to force the blood through, right? Blood started to get stuck in his blood vessels. And he almost died. He had stroke, he had hepatosplenomegaly, where his spleen was almost completely obliterated, right? And he was done for the rest of the season after that. Now he came back the next year, but when they made it to the playoffs, they had to go to Denver again, right? Obviously, if you're a smart man, you are not going to play, right? Because you're under the same situations then if you play, right? You're going to be dehydrated, you're going to have low oxygen, right? What happened? He had to sit out. And most of the football players and most of the actual fans got on him for sitting out. It's a life and death situation for him, right? If he would have played, there's a high probability he'd have another Sickman crisis. He would die from this one. Right, so those are red blood cells. Look at how small the blood vessel, the capillaries are. So then the red blood cells have to go single file, so then you can give its oxygen away. Another example, and here's hemoglobin, right? So hemoglobin is a combination of proteins called globins. The main purpose of these globins is to have these little intermediate areas right here called heme. The globin chains, there's 2 alpha and 2 beta chains right here. These alpha and beta chains' main purpose is to stabilize heme. Heme is a chemical formula that allows us to carry iron. This iron then allows us to carry oxygen. Now, there are some kind of anemias, right? When you have this, right? This is our CBC. We talked about the white blood cell count. Normally with the CBC, we take blood out. We want to see if you are carrying enough oxygen. So what we're going to see is, what is your hemoglobin count? Hemoglobin count is a measure of how much capacity we have to carry oxygen. So this iron right here, the more hemoglobin, the more iron, the more we can carry oxygen. Perfect. The opposite's true. The lower the hemoglobin, the lower the oxygen carrying, right? So if your hemoglobin, right, for men, the normal should be 14 to 16, right? And that's, I believe the numbers are over here, way at the end, right? Where is it? Right? 14 to 18 for males. That's your normal hemoglobin count. For females, it's a little bit lower, right? 12 to 14, 12 to 16 for females. Now, the hemoglobin count right here is our oxygen carrying capacity. So this Hg is hemoglobin. And it's a sign of O2 carrying capacity. And what happens is, if your hemoglobin count is low, you're immediately anemic. It doesn't matter what my other count is. Hematocrit count is a percent of blood that is red blood cells, right? And that number usually is the same as your whole, or when we split it right here, right? This formed elements component, 45%. That's usually your hematocrit count, right? Now, obviously, you have other things except red blood cells, right? 5 to 10,000 of them are white blood cells. 250, 400,000 is platelets. But compared to how much are your red blood cells, that's a small amount. So usually your hematocrit is your formed elements. And usually 45 to 48% for males is normal. 42 to 46 for females is normal. Right? Always females a bit lower. Now, in terms of these formed elements, we're looking at it to see if you have enough red blood cells to carry oxygen. That's what we want to look at. If you don't, you're anemic. Right? Usually, both of these, hemoglobin and hematocrit, will be low when you're anemic. But there are some diseases where your hemoglobin is really low, but your hematocrit is normal. That does happen, right? People with iron deficiency anemia. Well, what happens? The problem is you're not getting iron, right? If you're not getting enough iron, hemoglobin is going to be very low. You're still producing red blood cells because you still need them, but the red blood cells don't have iron. All right, the red blood cells and the concentration is actually normal. But inside the red blood cells, you don't have enough iron in it. So you can't carry oxygen. You're still anemic. Right? So there are times when that does happen. Right. Now, I know you guys are getting tired. What time is it? All right. Let's talk a little bit about erythropoiesis. How we form it, and then we'll take a little break. Right. Take a look at this. Again, it's kind of cool. Right? It is very cool. But it's kind of complex. You make 2 million red blood cells a second. If you're making 2 million red blood cells a second, you need to get rid of 2 million. So where does that happen? It happens in the spleen. Right? The spleen receives 2 million red blood cells a second and recycles it. As it recycles it, the iron, right, starts to be moved in the bone marrow. That iron can be recycled and reformed and reused to make new red blood cells. Perfect. So in the spleen, iron is reused by breaking down the red blood cells. Now, red blood cells have a lot of proteins, the globin chains, right? The globin from hemoglobin is also recycled. It's just amino acids, right? So we can reuse those. The one thing we don't reuse, though, is the heme, is this area right here. This area right here, all these carbons and the nitrogens, that's the heme. That's not recycled, right? What happens with heme is this, right? And I'll redraw this chart in a second. With heme, right, so you have red blood cells, they go to the spleen. The spleen, right, reuses the iron and recycles it. The globin chains, the proteins, are broken down and the amino acids are reused. The big one is the heme. The heme is this right here. That needs a little bit of processing. This heme is turned into something some of you guys might have heard of. This heme is turned into bilirubin. Right? This bilirubin then goes into your bloodstream, into the liver. The liver takes that bilirubin and turns it into bile salts. Right? Now, why is this important? If you have kids, sometimes kids are born with jaundice. Jaundice is a yellowing of the skin and the sclera. Why are they born with jaundice? Simple, right? Usually we talk about it in terms of having, preemies, right? Premature kids. But even full-term babies or near full-term babies can have jaundice right when they're born. Congenital jaundice. Why? Right? Well, it's simple. In utero, has the baby in utero, in mom's womb, have they ever had to use the liver? No. In utero, they don't ever have to use their lungs because they're in fluid, right? So the lungs don't really get used, right? And the liver, right? We actually bypass those two organs. We have certain kind of blood vessels that bypasses the liver. Why? Because the liver doesn't need to be very important Because mom is taking care of everything. All the nutrients, right, mom is giving the baby. All of the toxins, mom is getting rid of from the baby. The liver never has to be functional in utero. So when you have a full-term baby, right, what happens? The liver here isn't mature, hasn't had to work, but they're still producing 2 million red blood cells. They're still getting rid of 2 million red blood cells. Before, when they were in utero, all this excess bilirubin, mom got rid of, right? Now, there's no longer mom to get rid of it, right? The liver has to be able to get rid of it, but it can't, not yet. Why? It's because the liver right here isn't mature enough. So then what happens? That bilirubin we produce by destroying the red blood cells, that bilirubin count starts to go up. As it starts to go up, right, all we do is wait, right? If the bilirubin's really high, we know it can cause mental deficits that last forever. So we will give them billy lights. We'll give them billy blankets. Lights, the main purpose is to get rid of the, right, of the bilirubin in your skin, decreasing the concentration. The main purpose, though, is to give the baby time. That time allows the liver to mature. And what happens? As the liver matures, the liver then is able to take that excess bilirubin and turn it into bile salts. Right? The baby itself is getting rid of the extra bilirubin. Now, this is why we don't worry about it much when kids are jaundiced. Right? It's just waiting for the liver to mature. Now, when you have an adult that's jaundiced, usually, do we give them billy lights? No, right? Why? It's because, that jaundice is a sign that the liver is failing, right? We don't have to wait it to mature, right? Those billy lights aren't going to be helpful. They need a new liver. That's the only thing that can get rid of their jaundice. Now, we see this all the time. We don't even think about it. How many times when you get a bruise, you can see the discoloration, right? What happens? Well, when you get a bruise, same thing here, right? You get the red blood cells stuck in the area where there's trauma. And what happens is, white blood cells, very similar to the spleen, the white blood cells go to the area where there's trauma, and they start to break down the red blood cells. In the process, that area that you have the bruise, right, you break down the red blood cells there, you produce bilirubin there. And what happens to your bruise? At first it looks kind of yellow, and then green, and then goes away. That's why. That's this process right there. All right, let's take a break, and we'll talk about your ABO blood group.